Welcome to Brain Vision.
Okay, so for this question, we can apply the energy balance equation, which is E dot in equal to E dot R. If we expand it, we have W dot in plus M dot H1 is equal to M dot H2. We know W dot in here is the power input from the PC components. And M dot here is the mass flow rate for the air. And H1 is the initial enthalpy for the air. H2 is the final enthalpy for the air. If we do some arrangement here, we have W dot in is equal to M dot times H2 minus H1. So in this question, we know the pressure is constant, which means that H2 minus H1 can be expressed as Cp times T2 minus T1. Cp is the specific heat of the air at a constant pressure. T2 is the final temperature. T1 is the initial temperature. So therefore, I have W dot in is equal to M dot Cp times T2 minus T1. And we know M dot, which is the mass flow rate here, can be equal to the inlet density of the air times the inlet volume flow rates, which can be also expressed as P1 over RT1 times P1 dot. P1 is the initial pressure, R is the gas constant for the air, T1 is the initial temperature in ranking form, since the gas constant in this case has a units ranking, and V1 dot here is the volume flow rates. So now we can plug in back to the equation. We have W dot in is equal to P1 times V1 dot over RT1 times Cp and times T2 minus T1. So we know the pressure is 14.7 psia, and the volume flow rate is 0.3 feet to the power 3 per second. We know the gas constant for the air is about 0.3704 psia times V to the power 3 per pound mass times Rankine. And the initial temperature is 70 degrees Fahrenheit, which can be also equal to 530 Rankine. And we know the final temperature is 83 degrees Fahrenheit. And we know the specific heat for the air at constant pressure is 0.240 British thermal units per pound mass times degree Fahrenheit. So now let's plug in back to the equation to determine the power that was dissipated. The power that was dissipated by the PC components. Okay, so we have W dot in is equal to P1 V1 dot, which is 14.7 psia times 0.3 feet to the power 3 per second, and then times Cp times 0.240 British thermal units per pound mass times degree Fahrenheit, and times the changing temperature, which is 83 degree Fahrenheit minus 70 degree Fahrenheit. And this whole thing here over RT1, which is 0.3704 psia times V to the power 3 over per pound mass times Rankine, and then times the initial temperature in Rankine form, which is 530 Rankine. And this will give us the power input, or the power that was dissipated by the PC components, is about 0.07 kilowatts. I'm sorry, not kilowatts. 0.07 British thermal units per second. So now let's convert it to kilowatts. So we know this is how we convert it. So 0.07 times 1 kilowatts over 0.94782 British thermal units per second. Okay. Since 1 kilowatts is equal to 0.94782 British thermal units per second, and this will give us the power inputs, or the power dissipated by the PC components, is about 0.074 kilowatts. And these are the answers for this question.